Dynamics and Newton's laws.
Hello and welcome to another class of physics. In today's lesson, you will be learning about Newton's laws of motion and how to apply these laws to practical problems.
In kinematics, we studied the mathematical description of motion. We looked at the definition of position, velocity, and acceleration, and their relationships and time evolution. Now, in dynamics, we are interested in asking the question, why do bodies move as they do? What causes a body to accelerate? Here we shall see that forces are responsible for acceleration.
To begin with, we must first define what we mean by a concept known as acceleration. Acceleration. If an object's velocity changes in either magnitude or direction, you know that something caused it to change. That which caused it to change is what we're going to learn in this class. But the mere fact that the velocity changes means that you have what is known as acceleration. So acceleration, which I will use the letter A, is represented mathematically as the change in velocity over time. Notice that for my A and my V, I am putting an arrow on top of them because acceleration is a vector quantity. What is a vector? A vector is a physical quantity which has magnitude and direction. Right? So we have a vector quantity which is a physical quantity which has magnitude and direction. There is another quantity which is different from a vector, which we also are interested in, which is known as a scalar quantity. A scalar quantity, unlike a vector which has both a magnitude and direction, a scalar quantity only has a magnitude. It's a physical quantity. Which has only a magnitude. In a previous class, we would have covered both what a vector is and what a scalar quantity is. An acceleration is a vector quantity, same as velocity. Now, we are going to ask ourselves, if an object moves, if I take an object and slide it on the table and it stops, or I take the object and let it hit this object, this other object here, you know from experience that the velocity, the reason why the object stopped must have been because of an obstacle or something that is causing it to stop. In reality, that which stops it is what is known as a force. And the force exists only when bodies are interacting with each other. However, once it's moving and it slows down or increases speed, it is because it is interacting with other objects. We are going to learn how these interactions come about and what causes them, as we have stated earlier, and the laws that govern them. All right, what we have here is an example of an object with a mass m that is moving from a position x1 and at a later time arriving at position x2 with a different velocity from v1 to v2. Obviously here the velocity has changed from its initial value to another value, v2, which can be greater or less. What causes the change, the actual change from v1 to v2 is what we are calling the acceleration, as is given by this relationship here. The cause of this acceleration is what we are now going to be focusing this class on. What causes the acceleration? Right? We will see that the cause of the acceleration is what we are calling force, and the force is the interaction of the force and the acceleration on the body is governed by three fundamental laws that we are going to learn today, and these laws are known as Newton's laws of motion.
The properties of force and the relationships between force and acceleration are given by Newton's three laws of motion. The first law describes the natural state of motion of a body on which no forces are acting. The other two laws deal with the behavior of a body under the influence of forces. Galileo Galilei, who died in 1642 of the Common Era, began the modern development of the science of mechanics. He studied and observed free-falling objects and noted that they had a constant acceleration. In addition, he noted that this acceleration was independent of their weight or mass. He performed these experiments at the famous Leaning Tower of Pisa. In the same century, in 1687, Sir Isaac Newton developed and published his book known as the Principia Mathematica. There he outlined the laws of motion, as well as the co-inventing with the German mathematician Gottfried Leibniz, that branch of mathematics known as calculus. Newton incorporated Galileo's findings into a formulation of dynamics which is now called Newtonian mechanics. Newton's laws are not a perfect description of how nature behaves. It fails, number one, at the atomic and nuclear level. There you will need a different theory known as the quantum theory. It also fails when objects or bodies are moving with extremely high velocities, close to the speed of light. Here you will need Einstein's theory of relativity. To study dynamics, we must introduce two new concepts that were not required in kinematics: the concept of force and mass. Force is a central concept in all of physics. It is a vector quantity which must describe the direction in which it acts as well as its magnitude. In everyday use, a force is used to describe a push or a pull. Examples are a stretch spring, a rubber band, a taut cable, or ropes. All of these exert forces on objects. In liquids and gases also, these forces occur. For example, between the particles of the liquid and the walls of the container. These forces are known as buoyant forces. There are also forces between sliding surfaces. These are known as frictional forces. All these examples that have been noted are all collectively known as contact forces, objects in direct contact with each other. There are forces that fall under the category of action at a distance forces, where you have no direct contact between the objects. An example is gravity and the electromagnetic force. Newton's first law. Every object or body continues in its state of rest or in uniform motion in a straight line unless acted upon by an external force. Of course, this implies that if there are no forces acting on an object, the total force on it is zero, which itself implies that there is no acceleration on the object. Remember, force is mass times acceleration. This therefore implies that the velocity of the object or body is constant. It has a fixed direction and a fixed magnitude. Most bodies we normally see stop when left alone. For example, in the presence of frictional forces. Or air tracks, for example, give a hint of the persistence of motion. Particles in a vacuum or celestial bodies such as the moon, asteroids, and other planetary bodies or other celestial objects or bodies persist in a state of uniform motion. A body with no forces acting on it is called a free body. Newton's first law is also known as the law of inertia because it expresses the tendency of bodies to maintain their original state of motion.
If I have an object and I slide it on the table, it stops. Newton's first law says that the reason why it stopped is because there is an external force acting. Imagine the surface now becomes, instead of the surface of the table, it's something like ice. Then if I was to push this object on the surface of ice, it will slide even further down, but eventually it will stop. So that is telling us that perhaps then we can get an idea that the force of interaction that is causing the object to stop on the table is greater than on ice. So one can think of a situation where we can eliminate that force of interaction between the object and the surface. For example, where we can actually create the object to be floating on air so that when it is pushed, it will continue to go even further and further away. And eventually it will stop only because there are air particles and air resistance that will eventually make it to stop. But in principle, it will continue to go on and on unless a force causes it to change its motion or it stops. This is the essence of Newton's first law. Now, the second law states that the acceleration of the object, that is the change in velocity over time, the acceleration of the object is directly proportional to the net external force acting upon it. In mathematical language, it can be represented as F, which is my force, and A, which is my acceleration. I have a proportionality here, so I can say that A is directly proportional to F. In other words, the acceleration is directly proportional to F. If I increase my force, my acceleration will increase proportionately. If I increase it by a factor of 10, the acceleration will also increase by 10, and so forth. Another way of saying it also in mathematical form is to write F is equal to the mass times acceleration, where the mass is a constant of proportionality. So this is the formula that we are going to use. Note that the statement says that we're not only interested in any particular force, we're interested in the net external force. What do we mean by the net external force? An object, depending on the body, it can be a human body or an inanimate object such as this. There may be forces that are inside, that are acting. We are not interested in those internal forces. We are only interested in forces that are coming to the object and acting and interacting with it from outside. These are called external forces. And the forces that act on our object can be more than one. It can be one force or